71% of the Earth's surface is covered by water. The remaining 29% is covered by land with mountains, forests, deserts, plains, and valleys. Surface waters include water bodies such as lakes and streams. Air pollution can have a direct impact on these water bodies and the aquatic life within them. Sulfur and nitrogen are two of the most harmful air pollutants to our surface waters. In excess, they can cause surface water acidification, which is harmful to aquatic life. Additionally, excess sulfuric and nitric acids can strip beneficial nutrients like calcium and magnesium from soils and surface waters and release aluminum at levels toxic to plants and fish. In surface water bodies, this can result in a reduced diversity and abundance of fish and other aquatic species, like plankton and invertebrates. These declines in aquatic communities can impact commercial and recreational fishing, as well as higher-order species like otters, minks, and loons, all of which depend on aquatic species for survival. Using critical loads tells us whether current levels of air pollution may have harmful effects. If you remember from the introductory video, a critical load is the level of deposition at which an ecosystem begins to experience harm. When a critical load is reached or exceeded, ecosystem damage is expected to begin. If the deposition of nitrogen and sulfur to a water body and its watershed is greater than the critical load, then the critical load is exceeded, and we can expect air pollution levels to be harmful to aquatic life. To calculate critical loads of acidity, we must first set an acid neutralizing capacity, or pH, goal for a water body. The acid neutralizing capacity, or ANC for short, is an indicator of how protected the water body is from acidic deposition. The ANC is the amount of bases minus the amount of acids in the water body. The acidic inputs from air pollution include sulfuric and nitric acids. The bases in the water are mostly bicarbonates that come from the surrounding soils. For a water body to be healthy, it must have enough basic inputs to protect it from current and future acid inputs. To protect a water body from acidification, managers and regulators can set an ANC or pH goal equal to levels that existed before human-caused pollution. Another option is to set an ANC threshold that provides overall protection for most aquatic life forms. For example, managers and regulators can select an ANC threshold to protect a specific sensitive aquatic species, such as setting an ANC goal of 20 microequivalents per liter to protect brook trout, or an ANC value of 50 microequivalents per liter can be selected to protect the overall health of a water body because it protects most aquatic life. After ANC values are established for surface water bodies, scientists, land managers, regulators, and concerned citizens collect surface water samples to measure water quality. This information is used to develop unique critical load values for each surface water body in the United States, as represented by the dots on this map. Each critical load is then compared against the deposition of nitrogen and sulfur from air pollution to determine whether the critical load for that water body is being exceeded. If the deposition exceeds the critical load, then we suspect surface water acidification is taking place. You may be wondering whether the streams and lakes in your forest area are getting better or worse with respect to impacts from air pollution deposition. Critical load exceedances for lakes and streams are examined with respect to nationwide air pollution reduction programs, such as the Acid Rain Program, Cross-State Air Pollution Rule, or other local programs. The great news is that these programs have reduced air pollution and acid deposition in some areas by over 80% since the 1990s. As a result, fewer critical loads are being exceeded within our lakes and streams. Scientists have determined critical loads for over 6,000 lakes and streams along the Appalachian Mountains from Georgia to Maine. In 1990, 50% of studied lakes and streams were receiving acid deposition in excess of their critical loads. From 2015 through 2017, only 7% of studied lakes and streams were still receiving too much acid deposition. That is an improvement of 86%. Fewer critical load exceedances mean fewer aquatic ecosystems are being negatively impacted by the deposition of nitrogen and sulfur. Although many lakes and streams are recovering, there is still work to be done. Maps showing us where critical loads of acidity for surface waters are exceeded can be used to predict where air pollution is impacting aquatic life in our streams and lakes. We can use this information to determine whether air pollution emissions are still high enough to be harming our waterways, and to guide decisions on how to manage and treat these sensitive areas. Reducing emissions is the best way to reduce the threat of surface water acidification from air pollution. But land managers can do their part. They can reduce activities that would compound this problem, because acidification is associated with a loss of soil nutrients. For example, limiting tree harvesting and minimizing soil disturbance in sensitive watersheds. In addition, land managers, like gardeners, can add lime to affected soils and surface waters to replace the nutrients removed through acidification. If we can restore the lakes and streams to their natural condition, native plants and animals will return, and the entire ecosystem, including humans, will benefit.